Okay, that's interesting.
But when you think geothermal, images that typically come to mind are things like geysers, volcanoes, ring of fire. That's conventional geothermal. We know the heat is underground wherever you go. We know with modern drilling technologies, we can drill to most of these depths, and we know we can create our own reservoirs to access this heat. What we're doing in next-gen geothermal is saying, that heat's down there. We're typically looking for temperatures of about 180 degrees Celsius or greater at a depth typically less than 20,000 feet. So we can use off-the-shelf technology and get the economics to work. And we're going down to that heat and creating our own reservoirs.
Land insights, market trends, industry experts. Welcome to the Land Department Podcast. The state of land and energy as we see it.
Brent, we're back at it with another episode, and we are probably in over our heads again today. We always try to get cutting edge topics, what's on the horizon, and I'll let you introduce Jason for us.
Well, we got Jason here. It's like everybody hears geothermal and knows generally what geothermal is, but Jason was kind enough to join us to really help us understand, what geothermal was and what it can be. And Sage Geosystems is a company that's really trying to push what geothermal can be and how it can be a part of our energy mix. So, Jason, thank you for joining us, man. I didn't have a connection with Jason in the past. Just reached out seeking information and asked if they'd be interested in doing this, and he was kind enough to do it. So, thank you very much. He comes from the oil and gas business, so we've got that little fraternity going. But yeah, Jason, welcome, man.
Thanks. It's great to be here. Thanks for having me. I know we've been talking about this for a few months now, so really glad the time's come to have the conversation.
We had a good laugh when we first reached out, and Jason called us. He's like, "Well, I'm like 2 months here."
Love this collage. We're going to be crayons and flip charts.
Yeah, he said, "I'm still trying to figure out how to get to the bathroom in the building." And I was like, "Look, let's pump the brakes a little bit, let you get settled in, and we can do this again." So I'm glad that worked out. But he's an old podcast head now. He said he's done 4 or 5 since then.
I think this is number 5. So, it takes a little bit of time to get the hang of it, but we'll get there and moving along.
Oh, you're an old pro by now, man. Old pro.
We'll see what you're saying at the end, right?
Yeah, that's right. Well, you're talking to a bunch of landmen, so it's going to be okay. So tell us about just the history of geothermal technology, maybe traditionally what it was. I mean, we all know geologic orientation, the hot spots and things like that, but what's today's geothermal look like?
For sure. So, many people will have obviously heard about geothermal, right? But when you think geothermal, images that typically come to mind are things like geysers, volcanoes, ring of fire, steam coming out of the ground. That's conventional geothermal. So you'll find that in places like Iceland, sectors of California, Nevada, but that represents such a small portion of the total geothermal resource. It's about 2% of a resource in the US. And so while geothermal is a component of the energy mix, it's a very small component just because it is so limited to those geographies and those geologic structures. And what we're trying to do now in next-gen geothermal, you may have heard hot, dry rock geothermal, is expand that footprint and expand the role of geothermal in the energy sector. We know the heat is underground wherever you go. We know with modern drilling technologies, we can drill to most of these depths. And we know we can create our own reservoirs to access this heat. And so that's what we're trying to do in next-gen geothermal and hot, dry rock geothermal.
Yeah. So how does that technology, where's that technology come from? I mean, obviously you're you have an oil and gas background. How does that skill set and what the oil and gas industry has learned and developed and advanced over the years, how is that applying to the next gen geothermal that you're speaking of?
So it's enabling it. And I think this is much of the technology development in oil and gas is what's driving the new technology in next gen geothermal. So if I just step back and look at conventional geothermal. So what is conventional geothermal? It's you have shallow pools of basically naturally occurring hot water. And what conventional geothermal would do is drill 2 wells into these pools of hot water and pull the water out, harvest the heat, put it back in, and just keep repeating that cycle. But that's why it's so geologically and geographically limited.
Limited.
There aren't
Yeah.
many places you're going to find that shallow pool of just naturally occurring hot water. So using oil and gas technologies, what we're doing in next gen geothermal or hot dry rock geothermal is saying, that heat's down there. Can we find that heat at an economic depth? And we're typically looking for temperatures of about 180 degrees Celsius or greater, at a depth typically less than 20,000 feet. So we can use off the shelf technology and get the economics to work. And we're going down to that heat and creating our own reservoirs. So through fracking, you can basically create that reservoir, that lung in the subsurface.
Okay.
We fill it with water. That lung expands. That water is heating up. And then we use the well pressure. So we start to let that lung close on itself and exhale, brings that hot water to surface. We harvest the heat, maintain the pressure in the system, and then re-inject it, allowing it to reheat.
Okay.
So that whole process is really enabled by technology developed in oil and gas, particularly in onshore and conventional plays. And that's what's really helping improve the economics and expand next gen geothermal.
Yeah. So is the premise behind next gen geothermal still a dual well system, an injector and a producer?
It is. And so when you're thinking about next gen geothermal, you'll have 2 wells. You still have that injector and that producer. Now there are different systems that are currently being developed in this. So one is called closed loop. So in closed loop, you're drilling multiple laterals in the subsurface, 2 wells right next to each other. And then you're basically connecting them at the toe of the well. And you're pumping water down one, letting it naturally heat in that pipe surface area, creating an underground heat exchanger and producing it back to surface. So there's no fracking involved in that. There's a lot of drilling, a lot of steel going into the ground to create that surface area. There's enhanced geothermal, which was developed in the 1970s by the DOE, where they're drilling 2 wells and they're connecting them in the subsurface via a frac system. And in that case, you're pumping down one, you're going through that frac network and up your producer.
Yeah. So obviously, if we're talking 70s, those would be more conventional, maybe somewhat of a lateral, but not horizontal drilling in the way that we think of it today. Is that horizontal
So when
fracking?
So when it started, it was vertical. So you go to in the DOE area called Fenton Hill. These were vertical wells joined together in the subsurface. EGS today has now made those into horizontal wells with large unconventional style fracs connecting them. So that's the second technology of next gen geothermal.
Yeah.
And the third technology, which is what Sage is pioneering, is called pressure geothermal. So we're still drilling 2 wells, but we're not connecting them in the subsurface. We connect them at the surface. So each well has a near wellbore frac, that lung reservoir analogy. And then we just operate it like a 2-cylinder engine. Hot water is coming out of one well. We take the heat, keep the pressure in the system, which increases our net output. And then that water gets injected into the colder well where it reheats, and we repeat that cycle 1 to 2 times per day.
So you're flowing up from one, running it through your plant, injecting the cooled water into the other, and so you're essentially filling each bladder independently, right? If in layman's terms.
That's correct. So each kind of reservoir, each lung has a base volume of water in it that we inject, the pad in kind of frac terms. And then we cycle about 20% of that water. So 80% of the water still stays down there hot.
Okay.
So pulling about 20% out, extracting the heat. We're not bleeding off the pressure, which is a big differentiator. It's why we call it pressure geothermal.
Okay. That makes sense.
And we use that pressure to get the water down the neighboring well, where it mixes with the 80% hot water, which helps in the reheating process.
Okay, that's interesting. So So it's not in the way you think that historically you would have, to your point, the dual laterals where you frack and you're just depleting the water and it's moving and flowing through those fracks. This is an independent, two independent systems that you're recharging. What you mentioned, 2 times a day.
That, that's still being modeled. What we would expect is 1 to 2 times per day that it will switch, like that 2-cylinder engine.
Interesting. So you guys are developing and growing this technology, this latest generation of technology, and right now, I presume what you guys have. We've talked about dual systems or a 2-well type system. How do you scale that type of technology, or how do you guys foresee scaling that? Is it just multiple 2-well systems, or do you see being able to grow these 2-well systems into multiples of 2? A 4-well or 6-well or an 8-well. Is that something that is in the vision for this, or does it not work that way? How do you grow it?
So it definitely works that way. So that's one of scaling the system is one of the ways you can drive down the cost per kilowatt hour of energy coming out of it. And to get to scale for geothermal power generation, you really want to create those systems that are 150 megawatts, 200 megawatts, and greater, because there you can really get economies of scale. You can get economies of scale in the equipment you're ordering.
Exactly.
You get economies of scale in land use and the amount of space you're needing.
Mm-hmm.
So one of the biggest takeaways from the oil and gas industry, so of course there's the subsurface drilling and completion elements, but on the surface, there's the multi-well pad drill. And that's what you would recreate in the scaled environment for geothermal power generation. So you're not just going to drill 2 wells. You're going to look at multi-well pads. Maybe you're going to put 10 wells on a pad.
Yeah. Okay.
That's going to save you cost, because now you can mobilize one rig and walk the rig. You can do offline activities. The footprint of geothermal, you're looking for a 50 megawatt system, probably about 10 to 15 acres at the surface.
Okay.
And in the subsurface, we would kick the wells out and get the separation we need. But it's that small surface footprint. It's that ability to pad drill, that ability to get economies of scale that will allow this to scale up and grow.
Yeah. So you mentioned that kick out. That was kind of leading to my next question is, what is your, in oil and gas, we think of spacing. How much can I produce from this well, and how much can I produce from a neighboring well without affecting my production for my first well? What does that look like in geothermal? Is it dependent upon the temperature of the rock that you're drilling to? How big of a subsurface area, I guess, would you need if you were going to do a 2-well system, or even a 4, 6, or 8, or 10, like you mentioned? What are you anticipating there?
Yeah. So as we start modeling the behaviors, the potential interference or frac rate from one well to the other, I think that's one of the benefits of the pressure geothermal system is what we're doing in our approach is what we call gravity frac. So we're fracking primarily initiating that growth downwards and then out. And that keeps that frac a bit more consolidated near well bores. From a spacing area, you wouldn't anticipate a larger subsurface spacing or footprint than into oil and gas development. We're still trying to get into that exactly what does that spacing look like. We do have a range, but it would look similar or less than that oil and gas route. Because again, trying to keep that frac near well, it's one of the ways you're improving the efficiency of your system.
No, that makes sense. And I'm sure, like many of and I air quoted new energies projects that we're seeing, the CCS type stuff or CCUS, and what you guys are working with, the lithium extraction through brine that's going on. The rules of the game aren't necessarily in place yet, from a regulatory and permitting standpoint. So I guess at this point, you guys are working within your lease agreements or whatever your agreements are to provide you sufficient space to do your pooling or spacing. Are there any developments from the regulatory side of things that you're privy to that are advancing and growing, or are you guys really having to work with legislators to help inform them to build the rules?
It's definitely a mix. And so it's going to be very dependent on where you are. So I can't speak to every,
Sure.
geography. But each state's going to have its own view. If you're on federal land, that's going to be a different type of regime as well. Much of what Sage has done initially is we started our first operations in Texas. Reasons we do that is, as a startup, we want to be able to get to the field quickly. And
Mhm.
Texas has a very mature permitting and regulatory regime when it comes to oil and gas. They know how to permit wells quickly.
Very
And there's a
business as well.
acceptance for what we're doing as well. And so that really helps expedite the speed to getting something online. So we just our first commercial project was actually a long duration energy storage project, which uses the same subsurface technology as geothermal. It's a 3 megawatt facility about an hour south of San Antonio. And I'm mentioning that one because we took that through the permitting regime. And so we got firsthand experience of the process. So from a drilling permit, very short timelines,
Yeah.
permitted by the Texas Railroad Commission. So the same agency that permits oil and gas is permitting geothermal and our storage well.
Yeah.
We received our injection permit. We received documentation for pit operations. And so we've gone through that. Now, there were some, questions on the application that's like, well, this applies to oil and gas and not us. So there's definitely first of a kind perspective, a learning curve. But working together, we were able to move that process through, and it was great to see.
Yeah. Yeah. Well, I think Texas has made itself a leader in the space by being an open and friendly market to to companies who are trying to advance energy development. I mean, we see it. It's been a hot spot for, obviously solar and battery storage and wind projects have been a part of Texas energy mix for many years. And obviously, oil and gas is the king, here in Texas. But one of the more recent things, and Sage has had some really good press recently, is the data center boom and the expansive and extensive need for power. You guys signed a deal with Meta, or at least press releases went out. I don't know much about the details, but so how does that work? I mean, obviously they need endless power and a lot of it and consistent power. Do you, when these deals come together, and I certainly don't need the details of y'all's deal if anything can't be shared, but in hypothetically, when you have a data center or someone who's got a direct power purchase agreement with a developer like you guys, what drives the location of that data center and that project? Is y'all's technology such that you have a large area that you can work with, or do you have to really be tied? Is there still a geographic component to the location of those types of projects, or is it, hey, it's just a matter of how deep I got to go to be able to align with this existing data center plan that's in place?
It's a great question. So before I get into kind of the location drivers of these, I think you touch on a really good point, which is the market for geothermal. We see two really clear customer types for geothermal power generation. You mentioned the Meta deal, and I'll talk about that here in a minute. But hyperscalers, it's a clear market area. These data centers are coming online. We know the power demand's going to increase. So Goldman Sachs, I read an article and an analysis they had done, and it was about 160% increase in power demand by 2030 from data centers. That's a big
From
shift.
data centers alone.
The EIA is projecting electricity demand doubling by 2050. So between data centers, population growth, industrialization, power demand's increasing, hyperscalers need power. And so that is a big market where we see geothermal power generation. The second market that we're working with is the Department of Defense. And so Sage has done 3 feasibility studies now for geothermal power generation at different installations with the Air Force, Navy, and the Army. And the goal there is resilient power. So how can you get a fairly small footprint power source, either in a fence line or near a fence line, to be able to get that resilient power that can be connected to the grid, but it doesn't necessarily have to be connected to the grid.
But it can be
So we see
dedicated.
those as
Yeah.
two big markets. In
But that
terms of
makes sense strategically, I would imagine, right? You know, if
look,
America's under attack and they attack the grid, this is still dedicated power that can feed a Air Force base or Army installation or whatever the case may be. Is that the kind of the logic behind that?
resilient, defendable power. So I think
Yeah.
that's exactly right. And it's just recognition that demand on the grid is going to be continuing to increase, right? So how do we create that power source in the system? In terms of location, it really depends on where you are. The areas that we tend to look tend to have more continuity in heat. And so you're a little less concerned about, is it this exact parcel of land, or is it this parcel of land? In areas of the country and some of the analysis, it's much more sporadic. I think those are future areas for development that needs a little more analysis to figure out what the heat signature is in the subsurface. But ideally, you're in an area with fairly continuous heat within a depth range. And from there, you don't need to worry as much about the exact coordinate where you're going.
Yeah.
One subsurface feature you do have to watch out for are faults. So you don't want to intersect a fault with what we're trying to do, because a fault is a big lead path for that reservoir we're trying to create.
Where there's heat, you have things travel. Okay, so think of it more along the lines of an established, and I'm thinking in oil and gas terms here because we got a layman audience. Established shale area that is generally there will be production within a region of a particular area that consistently will produce heat that's not faulted up. So same kind of logic there would apply. Is that a safe assumption?
That's a fairly safe assumption.
Yeah, the devil's in the details, obviously, but
for sure. What you'd start to look at a bit more when you think location is a little bit less the subsurface attributes, more the surface attributes. So how far away are you from the right voltage of transmission line? Depending on the size of the facility you're building, you need a certain size line. So what kind of line are you looking for, and how do you build fairly close to that? Where on the grid can accept the power? Because you do have to go through a grid interconnect process. There can be an upgrade required. Understanding where on the grid you put the power meter, where is it simplest to interconnect, most efficient, cost-wise to interconnect, time-wise. Those are factors to start considering.
Yeah. Makes sense.
The other piece is, if you are in the middle of an established oil and gas area, that's helpful because it gives a wealth of subsurface data in terms of temperature. But you also got to make sure you're staying away from oil and gas wells. So different regulatory bodies have different clearances wired there. So that's one to keep in mind from the subsurface conflict.
Yeah, makes sense. So how would you, I have so many questions. How would you identify those areas? So, historically, if you think of an oil and gas development, you have seismic, you have well tests, you have well logs, you have all these things. If you're outside of one of those oil and gas producing areas, what is the source of information? Are you having to go out and do your own testing and prospecting of areas? Or is there government entities, or is there certain testing you could do at the surface level to determine what to expect subsurface? How's that process of prospecting work?
So there's a lot of data readily available for many parts of the country. So several universities and institutions have looked at temperature gradients in the subsurface across the U.S. And so there's a lot of just open data we can use. There's a lot of university data that we can use as well. Project Interspace, there's a big geothermal group that's really trying to drive and help improve the visibility, the viability, and the growth of geothermal.
Like the USGS, the USGS involved? Are there any government? Is there government support for programs that are doing some of this testing to open up viable areas on behalf of industry? Is there anything like that?
There is. And then there's university studies as well that look into this, that we can help. So in the feasibility studies we've done with the Department of Defense, there's a degree of open data you can use.
Mhm.
But then you can work with institutions that really know how to assess the subsurface. And so we work with the Bureau of Economic Geology at the University of Texas.
Okay.
They have access as well to a lot of well logs, a lot of temperature data, seismic lines. They can go acquire seismic lines as well that already exist. If you're in an area with none of that, it becomes a little more challenging.
Sure.
But that's kind of when you think about where do you want to start developing, you want to start more in an area with kind of a confidence interval of data, right? And what you'll find in the geothermal resource. So where do you find that heat at the economic depths? We are greatly expanding the footprint of geothermal with what we're doing in next gen and hot dry rock geothermal, but it's still heavily weighted on the western half of the country. The
Sure.
rock in the eastern half, you just got to go deeper to get to the heat.
Okay.
So western half of the country is still kind of your areas. South Texas, North Louisiana, Gulf Coast has a degree of viability as well and some good potential. But when you start thinking east, you're really not going to be thinking eastern half of the country for geothermal power gen necessarily.
At least today, right?
At least today. So there's a lot of work ongoing on how do you drill deeper. There's a lot of technologies being developed to be able to go deeper, and that will be a game changer in this when those are developed.
Yeah.
What we're trying to do right now is where can we get the heat using off-the-shelf technology?
Absolutely.
today?
Yeah. You talk about off the shelf technology. What about and this is the thing that landmen think of. What about off the shelf wells that have already been drilled? So are there scenarios where you can take a P&A well or a well that's getting ready to be pulled offline and re-enter that well? Or is it kind of one of those things that's cheaper to just do it right the first time and drill your own wells? Is there a strategy there or?
We get this question a lot.
Yeah.
Um,
Especially
and
people who are trying to dump a bunch of crappy well.
if you think about repurposing wells, there's a lot of cases to want to do that, right? For geothermal power gen, it's going to be more straightforward, more economic to drill a new well. And there are a few reasons why oil and gas wells are not really conducive to geothermal power gen. One, a lot of them don't necessarily go deep enough to the temperatures.
Yeah.
Some do, but
Yeah.
not all. They tend to be smaller diameter. So in oil and gas production, manufacturing, been trying to drive down the size of the wellbore. And for geothermal, you need larger casing. So most oil and gas wells are typically not going to be large enough. And then, of course, you have the integrity issues of existing or old producing oil and gas wells. So you have to do a lot of analysis on the pipe and the well to see what kind of integrity does it have. Can it last another, 20, 30 years?
Yeah.
Plus for what we're trying to do with it. When you start to look at all those factors, it's going to be more straightforward just to drill new wells.
Yeah. That makes a lot of sense.
With that said, Sage's test well that we started working with in South Texas a few years ago when we first started is actually an old oil and gas exploration well. Because it's exploration of a larger pipe, so it was usable and it was fit for purpose for what we were trying to do.
Relatively new enough.
Long-term producing, you're not going to find that necessarily, that attribute in a bunch of wells all close to each other per geothermal.
What does that casing size look like? So, does bigger casing equal better economics, more base load power generation? What's the equation there?
So power generation is determined partially by flow rate. So you need the bigger pipe to get the flow rates, to get the heat to surface at the rate you need to get utility scale power out of that.
Makes sense.
So you really need that larger flow rate without the friction losses in the system that smaller pipes can bring.
Okay, that makes sense. So want to step back a little bit. We talked about earlier, one of the challenges with grid-oriented type energy projects is that interconnect and the queue. And you mentioned how placement of your projects is affected by that location. We talked about direct purchase agreements and things like that with data centers and so on and so forth. Let's maybe expand upon that. Obviously everybody knows data centers is going to need a lot of power. and your system allows that kind of 24/7 base load potential to feed those systems. Beyond that, do you see geothermal being something that inevitably can scale to the point where it can provide constant, grid-based power? And if so, what does that look like? Is that a 15-year effort? Is it a 20-year effort?
Absolutely. So if you think, as I mentioned, conventional geothermal, such a small part of the current energy mix, just because it's so limited in where you're going to find it on the resource. The DOE did a liftoff report looking at next gen geothermal. So just to give you an idea of just how the size and the resource potential with this, 40 gigawatts of conventional geothermal potential, up to 5.5 terawatts of next gen geothermal potential. And that was the 130x increase. And that's per the DOE liftoff report. That gives you an idea of the size of the prize. And so as we continue to develop the system, as we continue to prove the commerciality of next gen geothermal and continue to demonstrate the scalability, clearly hyperscalers, data centers, that's a market, but you would expect to see this in many more areas as well. It's just part of the grid and a growing component of that grid.
That makes sense.
But let me just add to the kind of resource piece and the scalability and getting this into the power system as a consistent energy source. The scaling of geothermal power generation will be supported and enabled by the infrastructure, by the competency base that already exists in the oil and gas sector. So when I describe the technology to you, much of it has come from that sector. When you describe the large project management skills needed to build these facilities, the contracts and procurement skills needed, the land skills needed, that comes from the oil and gas sector. And so this is very much a strong complement and natural bolt-on to that sector. The service companies we're using are also being deployed in oil and gas. So the rig we used to drill our 3 megawatt storage well a few months ago, it was drilling an oil and gas well right before. And I saw it the other day, it's drilling an oil and gas well now.
Drill a well tomorrow.
It's in, right? We're not having to develop new competencies. We're not having to develop new service providers. We're generally not having to develop huge supply chains, particularly in the subsurface.
Sure.
And that's one of the big enablers that's going to allow this to really grow as we continue to work through and develop the technology.
So that leads to a good question. What is the key differentiator between 10 years from now a successful geothermal company and a not successful geothermal company? What is Sage going to have to do to separate itself, other than being one of the first and an innovator? Like, what technology really falls on, or advancements really falls on a thermal company to make this viable? You mentioned, I guess you got 60-70% of what needs to be done is already largely established and known, as far as the ability and the vendors and the support that you need to make your projects a success. But what falls on Sage to be successful?
So one area Sage is really focused on is looking at the entire system. We're not just trying to innovate in the subsurface with different frac designs or well designs. We're working to innovate across the full system, across the full subsurface and surface. And that comes from our oil and gas experience, that systems thinking, and our desire to continue to increase the output and drive down the cost per kilowatt hour. We have to continue to optimize, drive down that unit cost to really make this a sustainable power source in the grid.
Yeah.
That's one of the big differentiators. And so there are a lot of ideas out of improving the subsurface. But when you think about the surface, so what's been used up to this point? Right now, the base plan is to use existing off-the-shelf organic Rankine cycle technology. But that's a supply chain that's going to need to get built up to be able to deliver that equipment at the pace next-gen geothermal is going to need it. And so there's investment that's going to need to be made in that supply chain system. Additionally, there's going to be ways to optimize those systems. So instead of organic Rankine cycle, can you use supercritical CO2 in a different thermodynamic cycle? Sage is currently innovating in that space. Again, taking that systems approach, not just in the subsurface, but across the surface as well.
That makes a lot of sense. Let's shift a little bit and talk about who owns the heat, right? I mean,
That is a very important question, and people are like, "Oh, didn't think about that." So, I'm an important one, right?
yeah, that's right. I mean, it's so Texas is a mineral dominant state. Obviously, it's well established what rights fall within the mineral state as it pertains to oil and gas. We've seen with some of the advancements and different these types of projects and the growth and popularity and testing there that the devil's in the details. Who owns water produced for a brine project to extract lithium? Is that lithium a mineral estate item, or is it a standalone? Is the brine right standalone right like you see in Arkansas? What do we see for geothermal? I think the inclination as a landman is like, hey, that's a water. It's water being produced. That's a pore space thing. It's the surface owner. But what's the state of regulation, and what are the rules today on geothermal with respect to ownership?
It's very dependent on where you are. So it is state specific. And one of the biggest kind of areas to address is to be very specific in that point. Because before you really started thinking about next gen geothermal, expanding it beyond the geographies and geologies you find it today, that question didn't really come up in several states, right?
Yeah.
And so I think that clarity helps and goes a long way. In Texas, we are supported by a group, TexGeo, which is the Texas Geothermal Energy Alliance. And we have worked with the legislature through TexGeo, and heat is classified as basically not a mineral. So it's owned by the surface owner, just as you kind of mentioned there. So that simplifies this quite a bit in terms of when we're developing geothermal storage, power generation in Texas. That clarity is very helpful in that. And now you know exactly who you're working with when you start thinking about production.
Fantastic. What about from a geothermal lease standpoint? We've had a lot of federal land. You mentioned earlier, Western U.S. has obviously been traditionally the hot spot for geothermal leasing forms. Do you find in this space with next gen, as you expand out of federal lands, are there any additional considerations that Sage has had to deal with respect to negotiating those agreements, or has it traditionally been, for what you guys are doing, has it been business as usual? You're taking a form that works for a geothermal project in the Rockies and applying it to a surface owner, an individual owner that's not a government entity. Has there been anything along those lines that y'all have had to consider, or challenges thus far to factor in?
This is an area for sure that's going to continue to evolve as we do more of these. If we look at what we've done in Texas, we have the 3 megawatt storage facility, which is sitting on the site, the lignite coal plant. So we have a land use agreement there.
Yeah.
It's not going to look exactly like an oil and gas lease, right? But I do think much of the framework is probably going to follow into geothermal power generation. It's going to be some really good guiding principles in there, but each one's going to be a little bit different. I think as we continue to expand the projects, as we do more, as people become more aware of how geothermal power gen works, what the production profiles look like, those kind of things, that's going to start to get incorporated. So hard to really predict where that goes. But it has been done. So we
got something to work off of.
Megawatt, and continue building there.
Yeah. What's the life cycle of one of these projects? So, and this kind of comes as a landman thinking about agreements and terms and conditions of those agreements. How long does a project last? You drill and set your project up. Is that a 20-year life cycle, or is it 50 years? What does that look like?
So there's no reason why it can't be on the upper end of of the time range. What we model will model between 20 and 30 years. But this is, standard equipment with proven production history. So there's the benefit there to understand the lifespan of the surface. On the subsurface, with geothermal power generation, you do have a degree of thermal degradation over time. The difference, though, between conventional and next-gen geothermal is because in next-gen geothermal, we're creating that reservoir. So when it starts to cool over some time period, you can create another. So you can move up
So
the
another
well.
well. Yeah.
You don't even have to drill another well. Depends on your design, right? How we're trying to do it in the Sage system is move further up well and put another set of reservoirs in while the original set reheats.
That makes sense.
So there are ways to counter that thermal degradation with downhole systems and that kind of technology. In conventional geothermal, since you're dealing with that one pool of water, that's it. But in next gen geothermal, you need a plan to how to deal with it because it will occur. But each kind of technology is working through what that looks like.
Yeah. And that goes to your planning, right? Thinking about this, who's gonna win this game when it's all said and done is going to be the folks who really think through that. How can they maintain peak efficiency and production out of their each individual projects? And I guess it's that thought that goes into it.
That's exactly right, because you're not taking the heat permanently out, right?
Yeah.
But you need to give the heat time to get back to near wellbore, reheat the initial rock, and then get back into it.
Yeah. Jason, you mentioned a couple of times storage projects. Is there a difference between us? Like you mentioned a storage project versus a producing project. And maybe I'm using the wrong terminology, but really I'm just wanting to make sure that there's not some nuance there about that's oriented towards storage as opposed to just 24/7 constant base load type power.
So two different use cases, one common technology. So at Sage, we say we're developing and pioneering pressure geothermal. We call it pressure geothermal because we're not just using the temperature, but we're leveraging the pressure component as well. We're not bleeding off pressure at surface. So we're keeping that pressure in the system, which helps increase your net output. And that's that process of creating that lung reservoir, that inhale, expand it, the exhale, let it contract, using the pressure to get the fluid to you from the surface. That pressure component has energy. It's mechanical energy, and the temperature is thermal energy. In the case with that technology, we can have two distinct use cases. One is power generation, which we described here as the 2-cylinder engine. You're drilling the well deep to a temperature of 180 C and above because you need the temperature, and we're leveraging the thermal energy, but also that pressure. In storage, we're creating that same lung in the subsurface, but we're not using the temperature piece. We're just using the mechanical pressure component of it. And so what does that mean? We don't drill as deep. We drill as deep as we can go to about 100 degrees C. Why 100 degrees C? Because we don't want two-phase water at surface. That we then fill that lung with water. That water comes back, again, cycling about 20% of it, and it spins at surface for storage a Pelton turbine, which is like a big flywheel. The water hits a cup and it spins it, goes to a generator, power. That system doesn't produce its own power on its own, but what it does is you're storing energy in it. So we pull power from the grid when power is abundant and low cost. You can pull power from wind and solar and put it in the wall. So you use that to power up your pump, put water in the ground, store it. And then when you need it in the grid, so when wind and solar aren't on because the sun's not shining or the wind's not blowing, you now produce that up. Everyone, when they think storage, thinks batteries.
Yeah.
Batteries, they're like, that's the topic for storage.
Yeah.
Batteries are competitive with our system up to a duration of about 4 to 6 hours. At those low durations, batteries make sense. But when you have to start storing 6+ hours, that's when you need a long duration system. And that's the area we're working to get into. And that's where our system comes in. And so just kind of a bit of a comparison technology wise, depending on where you live, you may or may not have heard of pump storage hydro. Pump storage hydro is pumping water into a lake on top of a mountain when you have abundant energy. And then when you need energy, you flow the water down the mountain, spins this Pelton turbine, goes to the
Generates
reservoir.
power. Okay.
That's it. We're doing the same thing upside down.
Subsurface. Okay. Using the
Pump
pressure.
storage hydro is about 90% of the storage. Nobody ever talks about pump storage hydro because batteries get all the attention, but pump storage hydro is actually a really important long duration energy source. The problem is you only have it where there's mountains and valleys.
Yeah. And I guess reservoirs, right? Reservoirs that have, generation on the back end of those. Okay. Well, that makes sense.
Right.
I've never of all the talk about geothermal, I've never really dove into that or had
it's not
or looked at
that's
it and
right.
thought of it that way. It makes perfect sense.
That's right. So it's not power generation in the sense that you're using temperature downhole to create energy and surface. It's storing energy, bringing it back out of the ground.
Yeah.
Why do you need it?
Generation. Yeah.
You need it when we talk to utilities. The stats one utility gave us, and major utility in the Southeast gave us, was once intermittent renewables penetrate the grid more than 35%, you're going to need multi-day storage for grid stability. That's the market for long duration energy storage.
Perfect. So do you think the future of geothermal is going to be largely in the storage concept, or is it going to be more of the 24/7, direct service to data centers and maybe large municipalities and things of that sort? What do you envision?
I think it's a mix of both. So Sage's technology is positioned and designed for both use cases. All we're doing is varying the depth. And then, of course, you vary the surface equipment
based on need.
Based on need. One's you only need mechanical energy. One, you're trying to convert heat to electricity. So very different surfaces.
Makes a lot of
very
sense.
Similar surface. There's a need for both of those. And it really depends on the market. So I mentioned hyperscalers,
what the customer wants.
Critical infrastructure, power generation's needed. In the case of renewable energy developers that want to have 24/7 energy coming out of their system, in terms of utilities or grid operators that need stability in their system. Hyperscalers that want some wind and solar but need it to last. That's your market for storage.
Yeah, perfect. What's so obviously Sage is pushing the envelope on developing this technology. Have you started to and from a political standpoint, I know geothermal is gaining favor, at least with this administration and everything that I read. They're very pro geothermal. Have you started to see in this space other companies enter the space? Maybe your oil and gas companies having a geothermal kind of division, or these companies starting to think about how they can develop this technology and get into the game? Or is it still very much so forward that there's just a select few companies who are really trying to push it and make it work?
There's been a lot of interest in next gen geothermal, hot dry rock geothermal. And there's several companies entering the space, which is really strong to see, because if you really want to build the technology, get the attention on it, get the investment coming in, and have people talking about it, you need those entrants coming in, and you need that buzz getting created, because that's how you're driving the economics. That's how you're driving the supply chain.
Exactly. Yeah, I thought about supply chain for sure.
That full ecosystem to help drive the sport. And there are several companies developing different iterations of the technology or different systems to go after next gen geothermal. So it will be really exciting to see where this goes and how the different technologies play out. In terms of larger companies coming in, what you're seeing is some of these oil and gas companies are starting to invest in the geothermal space through new entrants like Sage and others as well, because it's a clear parallel to the work they're doing. It continues to build, like I said, on that competency base they already have, that knowledge they have, that supply chain and infrastructure that they have, and so it's a natural parallel. So it's exciting to see that investment coming in as well.
Yeah. Well, I think we're all excited to see it. I think it's everybody you talk to over the last 4 or 5 years where, renewables and alternative energy has started to gain momentum. You can't talk to anyone who really looks at things practically and says that geothermal, shouldn't have a place. And it makes a ton of sense. And I think, if any industry is going to innovate and make it viable, it's going to be the oil and gas business. And people like yourself, professionals like yourself with vast experience in oil and gas, are perfectly suited to tackle this new challenge. And man, we're just excited for the ride. We're excited as landmen to be involved and support the industry. And man, all in all, very appreciative of you taking some time to help explain to us just the, geothermal 101. I've taken a lot away from it, and I'm really excited to see you guys grow, and wish you all the best of luck, and wish you the best of luck. And I want to thank you for your time, Jason.
Thanks. It's been a pleasure being here. It's really exciting. I'm excited to see where this goes. We're learning every day. You hear about new companies working in the space every day. Feels like there's a new tailwind in the market fairly regularly. So it's very interesting to be a part of. It's great to be at the forefront of kind of that next energy wave, where we continue to develop energy sources. It's great to know that there's a whole system of competency and infrastructure behind its development. So looking forward to see where it goes. Thanks for having me.
Yeah, absolutely.
Enjoyed today's topic? Follow us on Spotify, Apple Podcasts, and YouTube. Learn more at dudley-land.com. See you next episode.